Who would have imagined that we'd have these problems in 2017? You know, in 2017, I would have assumed that we would just have to think and the pictures would show up on our screen. So when I was young, there were very different views of what the world was going to be like after the year 2000. And some of these were very optimistic, like the Jetsons. So I don't know if you have seen this American cartoon, but it was a family living after the year 2000, and technology gave them robot maids, and they could push a button and get their dinner. And of course, they had a flying car. There was a darker view of the future also back then in movies and books like Blade Runner, where technology was used for bad purposes, but they still had flying cars. So it's 2017, and I really want to know, where's my flying car? So if any of you have investments, you'll recognize this statement, that previous results are no guarantee of future returns. However, sometimes it's very useful to take a look at the past to try and figure out what predictions we made to see if the future came out the way we thought it would. So I look back to the year 2003, and I looked at the International Technology Roadmap for Semiconductors, the ITRS. This is an industry-wide consortium that both semiconductor manufacturers and semiconductor capital equipment providers and semiconductor consumable providers all participate in. And there's a test subgroup of that group, and in that group they decided that there were 10 different areas that were going to drive the future of the semiconductor test industry over the next 20 years, so from 2003 out to 2020. And I sat around with a few of the folks that I work with, and we graded that. We looked, okay, so it's 2017, we're close to the end of this period. How did we do as an industry deciding what was going to be important? And of those 10 trends, you can see that 2 of them came true the way we thought they would. Another 1, 2, 3, 4, 5 of them are sort of partial credit, that they came about to a degree but not completely. And 3 of the trends didn't come true at all. So let's look at these in a little bit more detail. The ones that didn't come true, the ones that came true most of all are designed to test EDA links. And this was a very important process by all the EDA companies and all the semiconductor manufacturers to try to improve time to market for very complex devices. So a lot of investment and a huge return in terms of being able to control the time to market as device complexity exploded. And massive parallel test. Massive parallel test has been essentially the drumbeat of the semiconductor test industry for the last decade, with SoC site counts doubling at least 3 times, and in memory doubling probably 6 or 7 times. So a huge success in terms of massive parallel test. Now, in test methodology, you can see that there were 3 things that were called for: new logic BIST, new analog BIST, and test embedded in the design process. None of those things came to pass. Logic BIST was important in the last few years of the 2000 to 2010. But even that was overcome by a consistent investment in structural test and improved methodologies in scan, which made it largely obsolete. So it sort of came and went. Analog BIST methods, this is where you design and the test embedded in design process. This is where you actually design in the measurement circuits into the device that you're designing so that you don't need to provide test equipment for it. This has always been a far more important thing to university professors trying to get tenure than to semiconductor executives trying to make money, because it doesn't solve fundamental issues around quality. Down in cost of test, test reuse is a partial credit. What we've seen in the industry is that the vision of test reuse across companies, across platforms has not come to pass, but within major semiconductor manufacturers, that significant investments into test libraries and test modules has yielded a tremendous return for mixed signal devices. So those are the partial credit ones. Now let's talk about the one, down in reliability screening. New acceleration technologies. This is essentially the notion, if you read the text behind this, that we could do away with burn-in test by using elevated VDD levels and essentially provide high assurance of reliability in the field by voltage stress testing devices. This has come to pass in the automotive segment, especially against microcontrollers, but has not become widespread. Now, the things that we got completely wrong, that cost of test was going to be driven by 100% DFT and BIS design. So these are parts that are designed so that you could just plug in a power supply, tell it to test itself, and it would tell you whether it was good or not. And that has not happened. We've actually sort of migrated a little bit away from that as device technology has gotten more complex. Back in 2003 was also the era where people were very excited about the idea of a common test language across different platforms and a common library for tests across platforms. And that is something that hasn't resulted in any practical technology in the industry. Finally, down cost-effective stress scaling. If you read the text behind this, it's primarily referring to wafer-level burn-in, which in 2003 was being positioned as a logical successor to package-level burn-in. That has not happened. It's really only taken off in areas where we are focused on known good die. So we got 2 right and the rest mostly wrong. By this, you might think that we've failed over the last 15 years. But over the last 15 years, we've been able to reduce the cost of test from 2.5% of IC revenue to 1% of IC revenue. So we've reduced cost of test by 2.5 times over that period of time. And we've also been able to maintain the same or higher quality levels for devices that are orders of magnitude more complicated. So when it comes to the important stuff, testing to quality and testing economically, the test industry has done what it's needed to do. And that's an important lesson for us looking into the future, that we need to look at trends that are going to make a meaningful difference in cost of test without compromising the quality of test. That those are the trends that I think are going to shape the industry over the next decade, things that can affect cost but not compromise on quality. If you look in the other parts of the report, there's some interesting things that they said that it was going to be, the things that were going to be most important in the industry were 450 millimeter wafers and 3D ICs for massive volume applications. So not so good on that. And I read through the report a whole bunch of times and I didn't see the word FinFET once. And I also didn't see anything about smartphones. So 2 of the things that have had the most influence in the SoC market over the past 5 to 10 years were completely missed. So there are always going to be things that we miss, and there's always going to be things that we call that don't happen. So if we're so bad at guessing about trends, why do we bother doing it? The main reason is because it matters a lot. Developing new ATE is very expensive. To develop a next generation digital instrument for an UltraFlex tester or a 93K or a T2000, it costs us about $60 million. Just the development of the ASIC is about a $20 million investment. even just the device power supplies are more than $10 million to develop. And the lead time to bring those from concept to market is over 2 years. Just a modification to an instrument can take us a year to do the design and the qualification before we can bring it to a customer. So if you end up with the wrong product for the market, it takes an extremely long time to recover. And if you did something in 2003, like betting your company on 100% DFT test, then it's likely that your company went out of business. Or if you bet your company on BIST, it's likely that your company went out of business. So it's important that you call the market right, and it's important that you know that even though the changes tend to be slow, that there are changes in the market that can affect what the market needs. So from 1985 to 1995, the most important thing in the SoC marketplace was better edge placement accuracy. It was all about edge placement accuracy, had a big impact on yield, and yield was a much bigger portion of the lost revenue than the cost of test. So the most accurate tester you could get is the tester that you needed. And in 1995, Teradyne came out with a Tiger tester, which was optimized for that world. And it turned out that the world was now turning towards digital and SoC mixed signal testing. And from 1995 to 2005, the world didn't care as much about edge placement accuracy. It cared about being able to integrate additional mixed signal functions. And then from 2005 to 2015, now the focus was all about trying to scale the site counts, getting to higher parallel tests. And if you have the wrong tester in any one of these intervals, you end up losing share. And you end up losing business at your customers. So now the job is trying to figure out what's going to happen in this decade. Is it going to continue to look just like 2005 to 2015? Or is it going to look different? To make things harder, we're at a very confusing time in the semiconductor industry. Back in 1995, there was a whole range of high volume end products. There were DVD players and game consoles and digital still cameras, digital televisions. There were iPods, computers, laptops, cell phones. And all of them drove a significant amount of ATE purchases. And then in 2007, the world changed. With the introduction of the Galaxy smartphone and the iPhone, all of a sudden the primary engine for the whole semiconductor test industry became mobile electronics, became mobile phones and smartphones. And so from 2007 to 2017, the world's needs for testers was very clearly defined. They needed testers that would support higher site counts. They needed testers that would support processors that had larger pattern memory requirements. They needed us to support the latest RF standards, and they needed us to support new power management technologies. But it was quite simple. In retrospect, looking back, it's quite simple for us to know what the market needed. But now we're in a new world. Now, the rate of growth for smartphones has leveled off. The complexity of those smartphones is increasing, but the volume increases are no longer happening. And there's a whole range of new segments that may or may not take off. There's manufacturing automation, Industry 4.0, smart buildings, smart infrastructure, wearable electronics, virtual and augmented reality, advanced driver assistance systems, and self-driving cars. All of those are on the horizon. And every single one of those markets has advocates that predict that they're going to be the next big thing that's going to transform the semiconductor industry. The problem is each one of these has unique requirements for technologies. In manufacturing automation, there's a huge demand for embedded power microcontrollers. Smart buildings and wearable electronics, it's large numbers of very low complexity RF interfaces. virtual and augmented reality, new screen technologies, new sensor technologies, and ADAS and self-driving cars, billion transistor processors going into automotive applications, and new sensor technologies like millimeter wave. As an ATE manufacturer, we're worried about this future because each one of those technologies could require a $20 million instrument investment to try to make sure that we're able to test. But some of them will not happen. So some of those investments are going to come to nothing. So it's a very risky time for us and a time where we have to be very careful about what investments we make. So this is a one-slide version of how Teradyne looks at the semiconductor end market to try and figure out what we should do. So remember on an earlier slide I talked about how the whole industry had gone from consuming 2.5% of IC revenue to 1% of IC revenue. So the first way that you look at the size of the market is just a percentage of IC revenue, and then you can break it down into segments. So here you've got the two big segments are PCs and mobile phones. So one may think, oh, okay, the important thing for an ATE company to do is to invest to make sure that you cover those two markets because they're so much bigger than everything else. But that misses an important point. People don't need more testers unless things are growing. So what's growing here? So in addition to just the size of the market, we care about how much that market is growing. So this is how much those markets are growing. So you can see over here we've got IoT growing at 13% over the next 5 years. And at the other end of the spectrum, you've got game consoles that are going to shrink 9% over the same period. So you can say, okay, we should really focus on IoT, on not game consoles. But that's not quite, that could end up with a distorted version of the world because you don't get an idea of how big the markets are. So if we combine them, you can start to see how much more revenue there's going to be in each segment. So mobile phones, a lot more revenue, automotive, a lot more revenue, IoT, a lot more revenue. So we can look at that directly, just the revenue growth over the period. And you can see now PCs went away. It's not as interesting a market for an ATE company. Mobile phones are very interesting. Automotive is now an extremely interesting market because of the growth in electronic content, and IoT is also important. But wait, there's more. These three markets, it's interesting. In mobile phones, in automotive, and in IoT. Each one of those markets is a big consumer of 16 and 32-bit microcontrollers. And some companies serve all three markets. And almost exactly the same microcontroller going into these three markets will end up needing vastly different amounts of test. So there's a test intensity. So if you're testing for medical applications, you need to be very, very careful and very, very thorough. If you're testing for automotive applications, not quite as thorough, but still a very high level of test intensity. And then you have things like mobile phones, servers, and set-top boxes. Below that, PCs. Below that, and digital TVs and IoT. So the same microcontroller going into automotive versus IoT, it's a difference of 3 to 1 in terms of the test intensity. So if you layer that into the revenue increases, you get an idea of how we see the market. And the way we see the market is the most important segment for us to be covering over the next decade is to make sure that we are well positioned to test what's needed in automotive. And even though mobile phones are not growing at the same rate that they were, it's such a huge market that it's still going to be one of the most important drivers for semiconductor test. So our main focuses are automotive and mobile phones. And look what happened to IoT. Huge growth, but it's on such a small base that it doesn't end up being a real needle mover for the whole market. So over the next 10 years, the amount of semiconductor content per car is going to at least double. It's probably going to be more than 2x what it is right now. The kinds of chips that are in cars right now are primarily automotive power and safety functions, these ASICs, and MCUs. MCUs all over the place. If you look at a car 10 years from now, there's going to be twice as much electronics, but there's not going to be twice as much of the stuff that's already there. It's going to be new stuff. There's going to be ADAS processors, which are like mobile processors, but tested to automotive quality requirements and working over automotive temperature ranges. Image sensors, dozens of image sensors, both in the visible and the IR spectrum, to try to provide data for ADAS systems, autonomous parking, and other functions. Radar sensors working in millimeter wave, LED lighting control, RF communications for vehicle-to-vehicle and vehicle-to-infrastructure communications, and multiple LCD panel displays, LCD and OLED for automotive applications tested over much broader temperature ranges. So just knowing that the automotive end market is going to be a mover is not enough. You need to understand the device technologies that are in it in order to map the required test. So this is automotive. So key things for Teradyne are we need to be good at processors. We need to be good at image sensors. And right now, Teradyne is the leading test provider for mobile processors in the world. We're leveraging that over into automotive. We're the leading provider of image sensor testers in the world. We're developing millimeter wave capabilities, and LED lighting control is essentially smaller power management devices that we generally cover with our Eagle product line. Now, IoT. So IoT, it's growing at 18%. That's fantastic. But if you look at IoT shipments, even in 2019, it's only going to represent 10% of the total microcontroller market. The microcontroller market buys about $150 million of ATE a year out of the $2 billion for all of SoC and the $2.6, $2.7 billion for the whole market. So less than 10% of the ATE market is microcontrollers, and less than 10% of the microcontroller market is IoT. So it's going to grow rapidly, and it's going to be important to be able to test those functions to be able to participate in the microcontroller market, but it's not going to change fundamentally the way the market looks. But IoT is a very broad impact on the overall semiconductor market. IoT is going to help drive 5G adoption worldwide because 5G technology has capabilities to provision very low data rate interfaces at very low power. So it's going to drive all the cellular networks to transition over to 5G. IoT will drive wireless backhaul. All the data aggregated from billions of sensors is going to drive backbone and cloud storage requirements. And IoT is also going to be the fundamental technology that underpins Industry 4.0. Collaborative robotics, mobile robotics, advanced vision systems, and factory integration are all going to be depending on IoT technology. So this is going to be more of a general market driver than an IoT device on its own. So having looked at that, what are the big questions that we're wrestling with? Over the next 10 years, will the migration of test time from package and final test to wafer test continue? Second, will devices spend more time on the tester or less? And there are two things that we're seeing over the past few years that we need to understand. One is there are lots of functions besides test that are happening on the tester, like trim, repair, security functions, crypto stuff, and also test time is growing for processors. I'll show you that in the next slide. Will device interface costs and technology limits really limit the site count and the progress in the market? I think this is a real threat to the future of the semiconductor ATE business, and I don't have a solution for it. will disruptive technologies change our industry? So right now, all RF devices are primarily tested by connecting hard to the RF ports. Is there a potential change to do over-the-air testing of those RF interfaces instead? Will we ever go from testing CSP and KGD devices on a wafer level to testing them as singulated dies? And is it possible that contactless parametric test will enable much better economics for reduced pin count test? And the most important question to me and to everybody that works at Teradyne is whether all of these things will end up making people buy more test equipment or less test equipment. So it's a very interesting position being in a semiconductor ATE company, because every day we put millions of dollars of engineering to try to drive down the cost of test and reduce the future demand for test equipment. And at the same time, we hope that other forces will drive it back up again. So we've got two minds going on about this. We know that our customers value cost of test, but cost of test going down ends up impacting our business in a very fundamental way. So this is a picture of the probe versus final. And it's just pretty striking to me that in 2005, 8 out of 10 UltraFlex testers that we shipped were used for package test. And in 2016, 3 out of 10 UltraFlexes that we shipped were used for package test. So the rest were used for chip scale packaging and for wafer sort. So a fundamental shift in the industry. And the question is, does this continue or does it flatten out? Test now includes more functions. So in a modern PMIC, up to 40% of the total test time is not testing the device, it's actually trimming the device to meet voltage specifications. And in testing a memory device, 20% of the time is associated with repairing non-functional cells so that you can work against a process that has a higher defectivity but much higher density. And in processor devices, good 10% is related to trim, calibration, and repair. Pruning out compute blocks that aren't working, repairing cache memories, and things like that. In many cases, if these functions were not done at ATE, the yield of these devices would be 0. Test fundamentally enables us to work at process geometries that would yield 0 unless there was this capability. And that investment in trim and that investment in repair is actually being included in that 1% cost of test of the device, and it wasn't in the 2.5%. So we're not only doing 2.5 times more than we were doing before, we're doing more stuff in that 1% than was being done in the 2.5%. So anyway, the point of this slide is that since 2005, in 2005, less than 30% of the total cost of testing a device was related to the device interface. By 2016, that's over 40% of the cost of testing a device is related to device interface, and it's the single largest cost in testing a device. So ATE is under 40%, and the amount for handlers and probers is actually decreased from about 25% to just under 20%. So this is consuming more and more, and there are two things that are driving this. One is increases in site count, and the other is the pitch, pad pitch at wafer sort, and the bump pitch for package test. And these are factors that have caused us to invest more heavily in our test cell integration capabilities, our technology, and we've actually even put in a clean room in our Agora Design Center so that we can set up and do integration of test cells to try to control and mitigate these. But it's a very significant I think it's a significant problem for the industry because it could stall out improvements. And those improvements are going to be very important because processors are the fundamental technology that underpin microcontrollers, mobile processors, automotive processors. Processor cores are increasing in number and increasing in complexity. And it's hard to see with the slide like this, but there are 3 curves showing how much circuitry there is to scan, and it's relative to back in 2010, I believe is the beginning of it. And there are 3 curves. This green one is actually low power microcontrollers. And then, so it's basically saying it's going to go from 1, it's going to be 10 times as much circuitry to scan over the next 10 years. Some of that is going to be taken up by compression. So compression is going to help reduce that, but it's only going to reduce it down to the point where it's 5 times as much scan that needs to be done. So that's a potential increase of up to 5x for processor-based devices. That 5x increase means that one of 2 things has to happen. Either we have to solve the device interface challenge and be able to get to higher site counts with reasonable cost device interfaces, or we're going to have to change the approach to structural testing of devices, because structural test scales with device complexity. So we've taken one thing. I'd really like to do the next slide in presentation mode if we could. So another potential solution to the processor test problem is to do 100% system level test. The issue to do 100% system level test is the test times are very long. 6 to 20 minutes to do system level test of a processor. In order to do that, you need to be at very high site counts. And in order to have very high site counts, you need to be able to do this in a way so that you can load and unload the devices asynchronously and also keep maintaining the sockets that you need to. So Teradyne has released a new tester, and this is a column of slots that you plug in essentially dual site device interfaces. And this up front is a little pick and place handler that puts devices into those sockets, and then there's a robot that moves the device interface and plugs it into the tester and then unplugs it from the tester, brings it back here to be unloaded. The advantage of this architecture is that since it's asynchronously loaded, it's always running. And since you get the chance to touch the device interface every time it's loaded, you can take bad device interfaces out of production without stopping production. So if you do a standard high site count interface, and those of you who do memory test understand this, that over time the number of active sites is going to come down as sockets get dirty, as problems happen, and then eventually your production management has to make the decision to take a test cell offline, get everything back working again, and then put it back into production. With this architecture, essentially, you have the capability for self-maintenance. And so you can stay at very high availability and very high throughput. So this is in production here in Korea, has been for the past few months. I don't know if this is the way the world will go, because this is a very expensive solution to try to set up for a device. It'll cost $1 million to just develop the technology to put one part on this tester. But if it's a very high volume part, it justifies it with the overall economics of being able to do system level test with such a high site count. So, since we were so wrong predicting the future from 2003 to 2017, I thought that I would make some guaranteed predictions for 2022. And I'll come back here in 2022, and you can give me a report card about how well I did. So here's what I think is going to happen over the next 5 years. I think parallel test is going to continue. Site counts are going to increase. Some high volume segments are going to double over the next 5 years. But more and more devices are not going to have enough volume to justify doing increased site counts. So there have to be other solutions. The total market for ATE for automotive, including high power, is going to be bigger than the TAM for mobile by the year 2022. Right now, the total market for mobile is probably 5 times as big as automotive. By 2022, I think they're going to be flipped, that mobile is probably going to be a little bit bigger that automotive is going to be a little bit bigger than mobile. I think that the drive for higher quality, lower DPPMs is going to continue because people like Samsung and Apple and Huawei are going to be competing for customer satisfaction, and they're going to be driving very high quality requirements. I think non-traditional test methods are going to be critical to try and get to these tougher, acceptable quality levels. And that includes both system-level test and that trend that was called way back in 2003 of extended voltage test. So high voltage stress testing of CMOS devices. In 2022, the most important instrument in a digital tester is going to be the power supply, not the digital. It's all about power supply accuracy and power supply response. That's going to be the most important instrument. And cost of device interfaces is probably going to be 50% or more of total cost of test by the time we get to 2022. Singulated die is not going to happen. There are people that will say it'll happen. We'll be using it for quality assurance purposes, but it's not going to be used for high volume manufacturing. 3D IC packaging is still only going to be used in high cost applications. GPUs, servers, and niche applications. It's not going to be broadly used for a lot of different technologies. DFT strategy is going to be just basically the same as it is now. And frankly, that's basically the same as it was in 2003. Structural test and compression. I think over the next 5 years, automation is going to begin to reshape the back end of the semiconductor industry. If you look at the semiconductor industry, the front end is highly automated, lights out factories, wafers moving in FOUPs along conveyor belts with very little operator intervention anywhere. As soon as you get into the back end, there's thousands of people pushing around JEDEC trays on carts. And with the new automation technologies of collaborative robotics, mobile robotics, advanced vision, and factory integration, there's an opportunity to retrofit existing back-end operations with automation to try and reduce labor costs and improve quality. And finally, your boss will still think that test doesn't add value even though it does. So with that, thank you very much. I appreciate your attention, and I appreciate your attendance at this conference and your participation in the test industry. Thank you very much.